Hi, this is the Science Chef. This is the second part of our 4-part series on chemical equilibrium. And in this video, we'll be looking at the catalyst principle and the factors that affect the equilibrium position of reversible reaction. So you want to know everything about the catalyst principle and the effects of temperature, pressure, and concentration on the equilibrium position of a reversible reaction. Then don't touch this channel. I will be right back. All right, welcome back. In the first part of this series, we looked at the basic concept of reversible reactions and dynamic equilibrium. In that video, we looked at the definition of equilibrium, then the definition of reversible reaction and dynamic equilibrium, also the conditions for a system to attain dynamic equilibrium. If you are yet to watch that video, check the link in the description. All right, so let's dive into this. The catalyst principle, what does it state? The catalyst principle states that if a system at equilibrium is acted upon by an external constraint, the system will react in a way that will annul the effect of that constraint. Now, this is similar to Newton's third law of motion in physics, which states that to every action, there's an equal and opposite reaction, right? That equal and opposite reaction in Newton's third law is similar to the reaction of the system that will annul the effect of the constraint on it, right? Now, that constraint is the action in the Newton's third law of motion, right? So, say system at equilibrium acted upon by an external constraint. In other words, if you distort the equilibrium position of a system at equilibrium, what will happen? System reacts to do what? To annul the effect. Similar to Newton's third law of motion, which says that to every action, there's an equal and opposite reaction. How? Now, this action here is what? Is the constraint acting on the system. While this reaction is the way the system will react to annul the effect. Remember, Newton said that to every action, there's an equal and opposite reaction. So let's assume that the action taken on a body is acting in the left direction, right? And the reaction will act in the right direction. And to be the same magnitude to the magnitude of the action. So that's exactly what the catalyst principle is all about. So because the forces are acting in opposite directions, they do what? They cancel out, right? The system will react in a way to cancel out the effect of that action. So what are the factors that affect the equilibrium position? 1, temperature change. 2, pressure change. We can say change in pressure. And 3, concentration change or change in concentration. Then let's just add a 4th one. Let's asterisk this one and call it effect of a catalyst. Right? Fine. So how does temperature change affect the equilibrium position of a reversible reaction? So in considering the effect of temperature change on the equilibrium position of a reversible reaction, we were analyzing this based on the energy change of the reaction. That's whether it is endothermic or exothermic. So let's start with an exothermic reaction. So For an exothermic reaction, delta H is less than what? 0. That's negative, right? So let's consider a hypothetical reaction. A plus B giving us what? C. That is an exothermic reaction. In exothermic reactions, heat is given out to the surrounding by the system. So it means that heat is what? A product. And an example of this type of reaction is the industrial manufacture of what? Ammonia, the Haber what? Process, which is N2 plus H2, 3H2, giving us what? 2NH what? 3 plus what? Heat. That's about minus 92 kilojoules per mole or thereabout. Fine. So now, in this type of system, what will happen when we increase the temperature? When the temperature of the system is increased, what will happen? Where is the temperature here? The temperature is the product, is it not? So if you increase the temperature, what are you doing? You are increasing the amount of the what? Products, right? And what will the system do? According to the Chatelier principle, the system reacts in a way that will cancel out that what? Effect. To every action, there's an equal and opposite what? Reaction, remember. So if you're increasing the temperature of an exothermic reaction, it means that you're increasing the heat. It means that your action is favoring what? The right side of the reaction. Your action is on the right side of the reaction. So what will the system do? The system will do what? React in the opposite what? Side. According to our Newton's third law of what? Motion. So the system will react in the opposite side. So the equilibrium position will shift to the left. And in shifting to the left, what will happen? It will cause this product to decompose to the reactant. You know, it will cause ammonia to decompose to what? Nitrogen and hydrogen what? Molecules. Are we together? Good. So let's put down some notes. Increase in temperature. An exothermic reaction does what? Shift the equilibrium position to the left, favors the backward reaction, and decreases the yield of the product. Simple. While the decrease in temperature will be the reverse of this. If you decrease the temperature, of the system, what are you doing? You are removing what? Heat, right? So if you are removing heat from this system, right, it means that you are increasing the reactant side of the reaction, is it not? Because heat is a product. So you are trying to lessen the effect of the what? Of heat. So you are indirectly increasing the amount of reactants in the system. So, and the system does not want that. So the system will react in a way to what? Cancel out your what? That effect. So it means that your action is favoring the reactant what? Side. So let's represent this as your action. That's the direction of your action, right? So the system now want to react in its own way, right? And the only way the system can react is in the opposite what? Direction, which is what? The product what? Side. Are we together? And so what does that mean? It means that by removing the heat, the nitrogen and hydrogen will be forced to react more, right? Or combine more to replace the heat that has been what? Removed. And in doing that, more ammonia molecules will be what? Produced. Are we together? So, which means that if you decrease the temperature of an exothermic system, the equilibrium position does what? Shifts to the right, favors the forward reaction, and increases the yield of the product. So that is how temperature change affects the equilibrium position of an exothermic reaction. All right, let's move on to endothermic reaction. For endothermic reaction, delta H is what? Positive, greater than 0. So, as usual, let's use a hypothetical equation. Since delta H is positive, right? In an endothermic reaction, heat is taken in from the surrounding by the system, which means that heat is part of the reactant in an endothermic reaction. But in an exothermic reaction, heat is part of the product. So, for a hypothetical reaction, we'll have A plus B plus heat, giving us what? C. Example of an endothermic reaction is the thermal decomposition of calcium carbonate. That's CaCO3 solid plus heat, giving us what? Calcium oxide and carbon dioxide or carbon 4 oxide. Fine. If we increase the temperature of this system, what will happen? By increasing the temperature of the system, what are we doing? We are adding more heat to the system. Is it not? And if you're adding more heat to the system, what are you doing? Your action is directly affecting the reactant side. So it means that you are increasing the content of the reactant in the system, right? It means that your action moves this way. Are you together? That's from Newton's third law of motion. Your action moves towards the left, which is the reactant side. So the system now, according to the Chatelier principle, will react in the opposite reaction in order to counter that effect, which will be what? The product side. Are you together? That will be the product side. And that, so by so doing, what happens? It will cause the calcium carbonate to decompose more to form what? Calcium oxide and what? CO2. So increasing the temperature of an endothermic reaction shifts equilibrium position to the right, favors the forward reaction, and then increases the yield of the product. Are we together? So that is the effect of increasing the temperature of an endothermic system. Now, what will happen when we decrease the temperature of the endothermic system? So if the temperature of an endothermic system is decreased, right, what will happen? By decreasing the temperature, we are removing the heat, is it not? And when you remove the heat, you are increasing the content of the product. So it means that your action is towards where? The right. That's the product side. And of course, the Chatelier principle says that the reaction will be in the opposite direction, because that's the direction that will cancel out that effect. Also, according to Newton's third law of motion. So it means that the reaction of the system would be towards the left. Are we together? So, which means that if you decrease the temperature of an endothermic reaction, it will cause the products to decompose back to the reactant. In our equilibrium position will shift to the left. All right, let's put that down. Decrease in temperature for an endothermic system does what? Shift the equilibrium position to the left, favors the backward reaction, and then decreases the yield of the product. These are the effects of changes in temperature on the equilibrium position of both endothermic and exothermic reaction. If you look at these points here, you will notice that they are similar to to a decrease in temperature in an exothermic reaction, right, at equilibrium. While these ones here are similar to the effect of increasing the temperature in an exothermic system. You know that an exothermic reaction is the opposite of an endothermic reaction. If the forward reaction for a given reaction is exothermic, then it means that the backward reaction is definitely endothermic. All right, so let's move on to the next condition, which is pressure.